When you turn your back on a coffee cup, you naturally assume it stays exactly where you left it. You navigate life relying on a silent agreement with the universe that physical objects remain solid, stable, and firmly rooted in reality, whether you happen to be looking at them or not. This photograph of the moon captures that intuition perfectly. We expect it to trace its orbital path through the night sky as a massive sphere of ancient rock, entirely indifferent to whether human eyes are turned upward to witness it. Classical physics treated the entire cosmos exactly this way, as a magnificent, predictable machine ticking away in the dark. But a century ago, physics peeled back the macroscopic layers of that mechanical universe and found a terrifying structural flaw. At the subatomic level, the cosmos stops behaving like a predictable machine and begins to respond directly and intimately to our presence. When scientists first isolated the foundational building blocks of reality, electrons, photons, single atoms, they didn't find smaller gears, they found matter that refuses to commit. In this photograph, Albert Einstein captures the profound unease of that era. The architects of modern physics had built the most accurate predictive theory in human history, yet they recoiled at what it implied. Einstein vehemently rejected a universe governed by chance, famously asking colleagues if they truly believed the moon only existed when they were looking at it. The equations they wrote described particles using something called a wave function. Before an electron is measured, it doesn't possess a definite location. It exists as a ghostly spread of infinite possibilities, exploring every path at once. That potential ends when we look. The exact moment a sensor attempts to record it, the wave function abruptly collapses, instantly snapping back into a single defined point. The math suggests that the act of observation actively bakes the physical world into existence. If you want to understand who or what is doing the observing, hit the subscribe button. The mystery only gets deeper. To see how concrete this anomaly actually is, we have to step out of philosophical debates and into the sterile control of a physics laboratory. This is an undeniable physical fact you can reproduce on a tabletop. The setup requires a barrier with two narrow parallel openings and a blank screen behind it. The emitter is powered down so low that it releases only one solitary electron at a time. Each particle travels entirely alone in a vacuum, with absolutely nothing to bounce off of. You would expect a single pellet of matter to go through one door or the other. Instead, the particle dissolves into a wave of probability, passes through both doors simultaneously, and interferes with its own alternate paths. Over time, these single solitary impacts build up a sprawling, zebra-striped pattern of bright and dark bands on the back wall. Desperate to see how a single particle could split its own path, physicists placed a highly sensitive detector right beside the doorways, designing it to quietly record exactly which slit the electron passed through. The instant that detector is turned on, the universe hides the trick. The interference pattern completely vanishes. The wave behavior is destroyed, and the electrons start acting like ordinary solid bullets, piling up in two simple vertical bands. The physical machinery of reality changes its behavior entirely based on a single condition, whether or not information about its path is being gathered by an observer. Looking at this complex array of modern sensors and wiring, the immediate instinct is to blame the hardware. It feels logical to assume that the physical bulk or magnetic field of the measuring equipment is clumsily bumping the fragile particle and forcing the collapse. But the mathematician John von Neumann pointed out a massive flaw in that excuse. A mechanical detector is just a collection of atoms. It is forged from protons and electrons, which means the machine itself must obey the exact same quantum rules as the particle it is trying to measure. When a particle in a haze of multiple possibilities interacts with a sensor, the math doesn't mandate a collapse. The sensor simply absorbs the uncertainty. The blur of probability infects the machine, travels down the wire to the monitor, and leaps straight into the human optic nerve. As long as that signal travels through physical matter, quantum equations never provide a mechanism to stop the contagion. The gray matter of the brain, constructed entirely of atoms, should theoretically join the massive web of overlapping probabilities. Yet we never experience the world as a blur. Von Neumann concluded that the chain of probability only stops when it finally reaches something not governed by physical laws, the subjective, invisible realm of human awareness. Consciousness becomes the required anvil upon which the wave function is shattered. This image captures the vast, sweeping scale of a cosmos we know to be roughly 13.8 billion years old. When we take the rules of the subatomic laboratory and stretch them across this unimaginable expanse of deep time, we run into a logic-breaking paradox. In the immediate aftermath of the Big Bang, the universe was a blindingly hot, chaotic expanse of bare nuclei and free electrons. It was a radiant, boiling fog, completely devoid of anything resembling biological life or a conscious mind. Over hundreds of millions of years, as seen in this stellar remnant, gravity slowly coaxed primordial clouds of gas to collapse. They ignited into the very first generation of stars, acting as massive nuclear furnaces to forge the heavy elements, the carbon, oxygen, and iron required for life. The specific atoms that currently make up your brain and optic nerves were assembled in those ancient stellar cores, billions of years before a single biological eye existed to open and look at the sky. If the strict rules of quantum mechanics demand a conscious observer to pull physical matter out of a haze of probability, how did the early universe physically exist long enough to forge the very elements that made the observers? We are trapped between two impossible realities. Either the first 13 billion years of cosmic history hovered in the dark as a mathematical phantom, patiently unrealized until our biological eyes evolved to look back at it, or the universe was always physically solid. If it was always solid, then logic dictates an unsettling necessity. The universe must have been continuously observed long before we arrived. To hold the physical architecture of reality in place from the very beginning, something must have been watching. In Part 2, we will follow the math into the deepest mystery of all, to see if the equations demand a quantum god. Modern physics contains a contradiction that threatens our entire understanding of time. Quantum mechanics suggests that reality requires an observer to become definite, yet the universe existed long before we arrived to witness it. At the subatomic level, matter refuses to commit. An electron or a photon exists as a wave of mathematical probability, smeared across multiple potential states simultaneously. This wave only collapses into a single measurable location at the specific moment it is measured. This creates a problem when we look at the cosmic timeline. The universe is 13.8 billion years old, while biological life occupies only the final thin sliver on the far right. For billions of years, ancient stars ignited and forged heavy elements like carbon and iron. These physical processes required matter to be definite and solid long before the first biological eye opened to witness them. Without a mind present to take a measurement, the early cosmos should have remained a ghostly blur of probability. The first stars should have existed as mere mathematical might-be's, rather than burning furnaces of nuclear fire. Science is trapped in a loop. We are the products of a physical universe, but the rules of that universe suggest it needed us to become real in the first place. Resolving this forces us through three radical exits. The first exit begins with the mathematical work of John von Neumann. He traced the chain of measurement from a particle to a detector to the human brain, searching for the moment a probability wave actually shatters into a fact. Von Neumann showed that every physical link in that chain, the machine, the optic nerve, the neurons, is made of atoms and should simply join the quantum blur. He concluded that only the subjective, non-physical phenomenon of consciousness possesses the unique power to force a collapse. This creates a logical necessity. Since we know the early universe successfully forged the specific atoms in our bodies billions of years ago, the von Neumann chain implies that an awareness must have been present to collapse those early states. This is the quantum God hypothesis. It frames God as a foundational consciousness woven into space and time, an infinite witnessing presence that occupies the vacuum and holds the entire ledger of cosmic information. Physical reality becomes a continuous manifestation in this framework.
The universe stays definite because it is being held in the gaze of an omnipresent witness, second by second. The second exit focuses on information. John Archibald Wheeler proposed that the physical it of a particle derives its existence from bits, binary answers to yes or no questions posed by an observer. Wheeler envisioned a participatory universe where the act of looking is the engine that generates reality. In his view, the cosmos remains a draft of possibilities until an interrogation by a conscious mind forces it to take a definite shape. Curious, we see the power of this interrogation when we point a telescope at a distant galaxy. We are deciding right now how to measure a photon that has been traveling for billions of years. As the delayed choice experiment demonstrates, our measurement in the present reaches backward across time. By deciding how to see that photon today, we retroactively force it to have taken a specific path through the ancient past. Human consciousness functions as a retroactive architect in this model. By observing the cosmos today, we are the active mechanism sculpting the physical history of the Big Bang out of raw probability. The third exit is the materialist counterargument, known as decoherence. It suggests that the observer was never a special requirement.
Our thought experiments imagine particles in a silent vacuum. The actual universe is a loud, chaotic storm of microwave radiation, cosmic rays, and colliding molecules. A fragile quantum state is instantly battered by this environment. The information leaks outward and is scrambled by the surrounding noise, washing away the interference pattern. A grain of dust colliding with an atom acts as an automatic measurement. The cosmos effectively measures itself billions of times a second through brute physical friction, with no mind required. In this view, the universe is a blind, self-correcting machine. It baked itself into a definite state long before life emerged, driven by the sheer density of its own interactions. Regardless of which theory holds, a century of quantum physics has ended the era of the objective, separate universe. Reality functions as an ongoing relationship between the observer and the observed. The rigid wall between the inside of our minds and the outside of the cosmos has been dismantled. We are built of star stuff. Every atom in your blood was forged in the nuclear fire of those ancient furnaces we once thought were unobserved. Human consciousness is a localized expression of the universe itself. We are a piece of the machine that has gained the ability to turn back and look at the gears. When you open your eyes and look at the stars, you are the waking universe. You are the cosmos finally achieving the awareness it needed to become real.